So let's look at the mechanism of this. This is an electrophilic addition mechanism. Here we have an illustration of a carbon-carbon double bond. There's a sigma bond between the two carbons, which is a result of the end-to-end overlap of an sp2 hybrid orbital on each carbon. And there's one remaining p orbital that's not hybridized on each carbon, and that one's vertically aligned. And the pi bond arises from the side-to-side overlap. This pi bond is more exposed than the sigma bond because it's more on the outside. It's weaker than a sigma bond because it doesn't overlap as well. And this is a good source of electrons for an electron-seeking reagent. So the pi bond is going to be the one that gets involved in this addition reaction. So here are two terms that are going to be important: electrophile and nucleophile. Phile comes from phileo, which is referring to love. Philadelphia is the city of brotherly love. Electrophile is something that loves electrons. So an electrophile is an electron lover. Electrophiles are electron-poor reagents, often cations. And because they're deficient in electrons, they are going to be attracted to the electrons, because opposites attract. Often these are cations which have a positive charge, and so they're going to be attracted to the electrons. And the opposite of the electrophile is a nucleophile, a nucleus lover. The nucleus is positive. That's where all the protons are. So a nucleophile is a reagent that is electron-rich. And these form bonds by donating electrons to electrophiles. The electrophile wants electrons. The nucleophile has electrons, and so they get together. So here we have the electrophile, a positive charge. Here's the nucleophile. It's got a lone pair and a negative charge, and it will donate its electrons to make a bond, and we'll get the formation of a bond. The double bond, oh, there's a typo. The double bond is a nucleophile. No, that isn't a typo. The double bond is a nucleophile due to its pi electrons. So we've got those pi electrons. We've got more electrons between those two atoms than normal. And so the double bond is electron rich. As the proton approaches, this is an electrophile. It's looking for electrons. We've got some electrons here, and so these electrons are attracted to this electrophile, and it will form a bond. The result of that now is that we have a carbocation over here, because this positive charge doesn't just go away. It's just getting shifted over here. So this pi bond ceases to be a pi bond, and those electrons are used to make a sigma bond with that hydrogen, the electrophile that's adding. Now, the carbocation, of course, is not very happy. Atoms that aren't happy are very reactive. The carbocation now has become an electrophile, and that will combine with the nucleophile to form a sigma bond. And so there we have the reaction of the addition of this hydrogen ion and this nucleophilic ion. And this is called an electrophilic addition reaction because the first step is attack by an electrophile. So I have this fantasy world, I call it Mrs. K's Chemistry Land. Disneyland's the happiest place on earth. Most students would not think that my chemistry land is the happiest place on earth. But it's kind of interesting sometimes. But in chemistry land, these reactions are all about different species, ions and reagents, and they're attacking each other, and the thing that they're fighting over is the electrons. So here, this carbocation is deficient in electrons and it gets attacked or attacks the nucleophile. The arrow here is showing the movement of the electrons, that these two electrons come over to make a bond with this carbocation. So let's look at that again. The nucleophile is going to be, if we're adding an acid, the nucleophile is going to be the anion. So here we have the electrophile. This is seeking electrons, and it attacks the double bond, and the double bond then forms a sigma bond with the hydrogen. Because this carbon now has lost the electron that it was sharing in that pi bond, it becomes a carbocation. So now this is an electrophile. This electrophile will attack this nucleophile. This chloride here from the HCl, plenty of electrons there. So one of these lone pairs of electrons is going to make a bond with this carbon, and we get this addition of HCl across the double bond. Sulfurous acid would look, no, it is sulfuric, sorry, H2SO4. The hydrogen attacked over here, forming the carbocation. Now the carbocation is going to go after the remainder of the acid, which is an anion, and it's going to make a bond using this lone pair of electrons over here. When we have the addition of water, oops, that's not the color I want. It needed, to do a hydration, we needed an acid catalyst. And that's because we get this hydronium ion, which is that's in the wrong place. It's over here. Which we can think of as being like this. So it's a hydronium ion is what an acid actually looks at, because a hydrogen ion is actually just a proton and is too small to be out by itself. So it has to ride piggyback on something else. And in an aqueous solution, it will be riding on the water molecule. So this is the hydronium ion. This hydrogen ion part of it will attack the double bond. This is an electrophile. It is seeking the electrons of that pi bond, makes a bond. And then what's left after we get rid of this guy is a water molecule. And so we've got the carbocation, and it sees these electrons and says, hey, we can do something there. And so it will form a bond over here. And then the hydrogen gets spit back out. And so we've got addition of water, hydrogen, and OH to that double bond.
And you said, what do you say you mean when you have addition of water?
An acid catalyst. The acid catalyzes it. So the acid catalyzes it, the water is added, the acid here is shown being released at the end because as a catalyst it doesn't get used up. A catalyst speeds up a rate of reaction, but it isn't actually used up in the reaction. The carbocation is going to be have a positively charged carbon atom. So we had sp2 hybrid orbitals, and one of these was overlapping with another carbon to form the sigma bond, and then we had this pi bond that was overlapping side to side. This p orbital overlaps to form the pi bond. And when it becomes a positively charged carbocation, it has lost the electron from its pi orbital. And so we've got these electrons all in a plane in their sp2 orbitals, and then we've got this empty p orbital. I don't know what else to say about that one.